Okay, so hello everyone, my name is Justyna Witulska, and I would like to present the results of the research about change point detection problem. In my presentation named Identification of the Structure Breakpoint for Independent Data with Changing Variance. And the presented results are the results of the common researches between of me and my promoter, Agnieszka Błońska, professor. And the aim of our research is to design a new method for change point detection and compare it with the other known approaches. And the main goal of this work was to develop a new method and check its correctness on the real and simulated data. And what is new? In general, a new method enables us to detect breakpoint even if the data exhibit non-Gaussian characteristics and the small differences between ratio of the standard variances in the first and the second segment of analyzed data. And this makes that the new method is more general than the other analyzed algorithms. And I want to also mention that the results of the research are described in the paper visible on the bottom of the slide. Okay, and the first is just why I start to explore the segmentation problem in case of change point detection. The reason is that segmentation is important common problem of various fields. For instance, it is used in case when we want to make seismic detection, if we want to analyze climate phenomena or some geomagnetic data or genetics. And moreover, it's also used in quality control and using information about change point, we can create more precise finite models. So it is a really big number of fields when we can use algorithms for change point detection. And what means change point detection in my work? We assume that we have a sample of independent random variables from some distribution, and the only one parameter that differs the random variables is the variance. So we have variance in some values when we have some, for instance, we have a sample and we have the observation 1, 2, 3, and n star, and they have one particular value of variance. And after that point, we have a different value of variance, and we can tell that this n star is the structure breakpoint in this case. And our research starts to implement algorithms known from the literature to change point detection. And on the right-hand side, we can see name of 6 algorithms that I used in my work. And if they have the values of p on the bracket, that it means that this method is parametric. And if we have n in the bracket, that it means that this method is non-parametric. And the statistics based on what these methods are created is visible on the right-hand side. And we have this research on this timeline that the first step was to make a simulation for the algorithm names from literature. And based on this, we conclude some conclusions that we used for create our new method. And we compare this, and we make the simulation again with our methods and compare with the results from the algorithm names from literature. And at the end, we confirm the universality of the process methodology when we analyze the real data measured by sensors. Okay, and as I said before, firstly, we make simulations for algorithms names from literature, and we examine the impact of factors visible on this slide to the result. And this was location of the change point in the random sample, sample size, the ratio of the variances in both segments, and data distribution on the separate segments. And these 2 last factors are the most influential in this case. And we have some interesting conclusions because one of this methods is the fastest than the others, so the optimization was possible. And moreover, for platikutic data, the best results are provided by non-parametric methods, and for remaining distributions, the best approaches are methods based on the statistics based on the likelihood function. And there was expectation. One simulation was made for data in which the standard deviations ratio in two separate segments is close to 1. Then methods based on the cumulative sum of squares are better. Okay, and on this slide you can see the not easy scheme for our new methods for detecting change points. And on the right-hand side, on the left-hand side, we can see the formulas for three statistics that we used in this procedure. And in general, we use one statistic A, what is connected with the standard deviations ratio in separate segments. And moreover, we use statistic B and C, what are connected with empirical kurtosis in these two separate segments. And this algorithm literally starts with the calculate these two statistics connected with kurtosis. And based on this, we decide if we have data what behaves like platypurtic distribution, distributed data or not. And if we say that this data behaves like platypurtic, then we go to this blue part and calculating the checkpoints using two non-parametric methods. And using one criterion connected with the quantile approach, we decide if we should delete this method, so say change point is not detected, or we calculate change point as algebraic mean of these 2 points. And if we have a situation when we do not have data from platypurtic distribution, so the data don't behave like this, then we calculate statistic A, and we can make optimization of algorithm using the fastest method. And after that, we calculate the change points using four methods, so Hawkins-Zamba method, binary segmentation, and these two approaches using also in this part. And next we have 2 criteria that can help us to decide if we should reject our change point or not, and if the first of this criterion reject the change point, that we also reject it. But if the second one not, then we calculate the change point as weighted mean using less algorithm than here. So we just remove the last one and calculate the average of this. And if these 2 criterion do not reject the change point, that we just calculate this change point as weighted mean from these 4 algorithms. Okay, so our approaches has 2 assumptions, and the first one is connected with this what I said earlier. So we have random sample, and this is random sample connected with independent variables. And the new approach utilizes statistics based on the sample kurtosis and empirical standard deviation. So for that reason, we assume that this theoretical fourth moment exists. Okay. First, we make the simulations for algorithm node from this feature, and we just have these conclusions that Hawkins-Zamba method is the best algorithm in most of cases. So we just compare this algorithm with our new methods when we repeat the simulation. And on the slide, you can see the results for data comes from Gaussian distributions, and on the plots B from generalized Gaussian distributions with parameters given in this way, that this is platypurtic. So as you can see, for each of the standard deviations our algorithm works better. So So this is a really good conclusion. And after simulations, we decided to make this test for real data, and we make 2 experiments, and we use sensors visible on the slide, so G-force meter, gyroscope, and linear accelerometer. And we had, as I said before, 2 experiments. And in the first one, we focus on humans. And we have this situation that human move from point A to point B, firstly slowly, and on some points he or she just starts to run, and this point is a change point of our algorithm. So the variance change point factor is the change of motion dynamics. And in the second situation, we have a simulation, not simulation, we have scenario when we focus on vehicles. So we focus on motorbikes and cars. And in this case, the variance change factor is the change of the surface. And on the bottom of the slide, you can see an example of this situation, so of second experiment. And as you can see, we have a different behavior of our signals when we have different position of our car and different moving kind. So firstly, we have on this situation the moment when a car leaving the car park, next driving on the stone road. Next, as we can see, the variance is slower because a driver starts to drive on the asphalt road, and next he just return to the back, to the parking. And the situation just is the same. So she or he should come back and drive on the asphalt road, next drive on the stone road, and next return to the starting point of our algorithm. Okay, and on the slide you can see example of real data segmentation by using this method known from literature. And on the yellow box we can see the real change point. So the period in which the real change point should be, and it includes the time of this. That, for instance, if I am observer of this algorithm, then I can say that the change point is on, for instance, 30 seconds, but I have some time of I can't be no exact because I have some how to say that moment of delay when I just stop it, for instance, in the stopper. Okay, and as you can see, the most of algorithms visible on the slide is on the yellow box, and moreover, new methods also is here. So this is a very good behavior. And after that, we just go to the last part, so to verification of our assumptions. And we checked if the data from both segments are normally distributed, if they are independent, and thus if the data in both segments have the same distribution. And we make it by using standard procedures visible on the slide. So I just look at this picture. There is angular velocity in the one particular sample, and as you can see, this auto-covariance function tell us that these data are uncorrelated. But if we just look at the statistics, what we obtain and the results of a statistical test, that we can see that the data from the first segment can be from the Gaussian distribution, but the data from the second segment couldn't be. And it is confirmed by visual inspection. Okay, and on the slide you can see the results for some samples. And on the first part of this table, we have just information about our samples. So what is a used sensor, in which period real change point is, and etc. And next we have the information about results obtained using different algorithms, and at the end using our new method. And if some points is given in the green box, that it means that this point is in the real change point period given here. And if it is orange, that it means that it's not in this period. And the gray boxes are connected with the situation when these algorithms reject change point. Okay, and the last part is connected with assumptions, and we have here information if we have Gaussianity on the first segment, on the second segment, and if the data are independent or not. Okay, so to sum up, in our research, we test various methods of change point detection for data with changing variance, and simulation test confirms the effectiveness of the new method, and the experiments based on measurements from the gyroscope and accelerometer confirms that the correctness of the method for real data, even if the data exhibit no Gaussian characteristics and the small differences between variances in separate segments of your. Okay, so thank you for your attention. This is my bibliography.